What's up, everybody? Welcome to another video lecture on the states of matter. In this one, we are going to talk about energy again, kind of like we did a couple videos ago when we were talking about how much energy it takes to cause phase changes. But in this one, we're going to look at how much energy it takes to heat a substance. But in order to look at how much energy it takes to heat a substance, we have to keep that substance in the same phase, because as we know already, as we cause a substance to change phases, to go from like solid to liquid or from liquid to gas or something like that, energy is involved in a different way than it is involved when we are not changing phases. So let's get in and talk about that. So the main heat equation we're going to look at is, I like to call it the MSHAT equation because it looks like the word MSHAT, but that's not really what it is and everything. So what we got going on here is we got Q, which is energy, is equal to M, which is mass, times the specific heat, which I like to use as SH, but that's not the real symbol for it. The real symbol for it is C with a subscript P, all right, for specific heat capacity. And what specific heat is, it's the heat that is required to raise 1 gram of a substance 1 degree Celsius. So it is different for pretty much every substance out there. And substances that have a high specific heat heat up very slowly, kind of like water, whereas substances with a low specific heat, like most metals, heat up quite quick. They also, if they heat up quick, they will cool down quick. If they heat up slow, they cool down slow. And then the final part is this triangle T, or the little triangle thing is a delta for change of temperature. And to find that, you take the final temperature from the problem and subtract the starting temperature, which means if the temperature is going up, this will always be a positive number. If the temperature is going down, this will be a negative number. All right, and this kind of determines whether energy is added in, when it's a positive number, or released, which is when the change in temperature is negative. So we're gonna see 3 little examples of this on the next slide, and then you're gonna probably get some to practice, and that'll be it here about specific heats and this specific heat equation. So what we're going to do now is we're going to look at 3 examples of this, and we're gonna use water, but we're gonna do one where water is ice, one is where water is liquid, and one where we have water vapor. And what you'll see is the specific heats for ice, liquid water, and water vapor are all different. In this first one, we have 10 grams of ice at negative 50 degrees Celsius, and I want to know how much energy it will take to heat it up to 0 degrees Celsius. So let's go in and take a look at what happens. So this is a Q equals MSHAT equation, or MCP delta T. And I just got to pull the right things out of the question. So the M is the mass. Mass always has the unit of pretty much grams, so there's my mass. My mass is 10 grams. So I take my 10.0 grams of ice. I'm going to multiply this 10 grams by the specific heat of ice, and there it is right there. It's going to always be given to you, or you can just type in specific heat of and name the substance if you're looking for it. Type that into the Googles and it'll tell you what it is. And so I'm going to type on in put on in here my 2.09 joules divided by grams times degrees Celsius, which is the units of specific heat. And their units are crazy like that so that everything cancels out. What we can see right away is those grams will cancel out. Finally, I need my delta T, my change in temperature. I'm starting at negative 50, I'm ending at 0. So remember, delta T is final minus starting. Well, the final temperature is 0. I'm going to subtract the starting temperature was negative 50. This is all in degrees Celsius. 0 minus negative 50 is positive 50. So my change in temperature is a positive 50 degrees Celsius, and so now I plug that in for delta T, and the degrees Celsius is crossed out. I now go take a handy dandy calculating device, take 10 times 2.09 times 50, and I get 1,045 joules is my leftover unit. In equation 2, we have 15 grams of water at 15 degrees Celsius, and we're going to heat it to 88. Again, I'm going to use MSHAT, and my mass, in this case, look for the grams, is 15 degrees Celsius. So let's plop that in for M. 15.0 grams. I might have said degrees Celsius a second ago. That was wrong. But it's 15.0 grams is my mass. The specific heat of water, again given to me in the question here, is 4.184 joules per gram times degrees Celsius. So I plug that number in here, 4.184 joules over grams times degrees Celsius. And this causes those grams to cancel out. The last part is finding my change in temperature, my delta T. Delta T, remember, is equal to the final temperature, which in this case is 88, times the starting temperature, which in this case is 15. 88 minus 15 is 73. And since temperature is going up, this is a positive change in temperature. I put in 73 degrees Celsius, and I can cross out the degrees Celsius. I then, take my calculator, do 15 times 4.184 times 73. What I end up with is 4,583.67 joules. All right, and if I wanted to round it to 2 or 3 sig figs, I then could do that afterwards. But let's worry about plugging and chugging in the formula right now. Finally, we have 25 grams of water vapor at 105 degrees Celsius. How much energy is required to heat it to 118? So again, it is the MSHAT formula. My mass is 25.0 grams. So put that in for mass. The specific heat of steam, or water vapor, is 2.03 joules per gram degrees Celsius. So once again, I'm going to multiply my mass by this specific heat value, which is 2.03 joules over grams times degrees Celsius. And my grams cancel. And now I just have to find that delta T, that change in temperature. In this case, I'm starting with 105 degrees, I'm going to 118. So it's final minus starting, final minus initial. So 118 minus 118 minus 105. 118 minus 105 is 13 degrees Celsius. So the change in temperature is 13 degrees Celsius. I now plug and chug everything into a calculator. 25 times 2.03 times 13. And what I end up with is 659.75 joules. And that's all you have to do to use this heat equation. This is a pretty quick one. You're going to get some practice problems after this, so kind of go forward with those. If you have any questions, reach out to myself or whoever your teacher may be, and we will be happy to answer these questions for you. And that is all I have for you. One more lecture to go in this lecture series on the states of matter. And you guys have a good one.